I shall start with just a few words to introduce our speaker today, Professor James Brusey, Professor of Computer Science at Coventry University and a member of our Computational Science and Mathematical Modeling Research Center, which is our hub for, shall I say, more fundamental computer science research within the university, but also supporting AI and data science research for the rest of our set of research centers, 18 of them at Coventry. James has been with the university for a number of years. He initially finished his PhD at RMIT in Melbourne, Australia, with a PhD in robotics and reinforcement learning. He came and joined my small team working on wireless sensor networks for most of the period 2006 to a couple of years ago, when he returned to his first love, reinforcement learning, to progress further some of the fundamental advances and industrial applications that he has been preoccupied with mostly for the past decades in that area of work. I look forward to be listening into the masterclass, and I wish him good luck. And the subject is not an easy one to convey, and I hope that we can all stay tuned and think really hard along James on the journey of learning about reinforcement learning and AI. There you go, James. We can't hear you.
I just asked him to unmute.
Need to sort. Okay, so I think we should have unmuted the audio now. So hopefully that's available.
Yes, yes, we can hear you well now.
Okay, so thank you. I've got this weird camera setup. So if you're wondering where I am, hopefully you have a little bit of a view of me from sort of above. But I'm just going to walk around and maybe gesture a little bit. Okay, so welcome to this masterclass on reinforcement learning. I had a number of options in terms of what material to cover. And I probably just need to give some background to that. I have previously given quite long courses on reinforcement learning, I suppose, several days worth of intensive time. And so I'm a little bit worried that I'm going to have a bit too much to cover here to try and get through it all in the 2-hour period. I'll try and keep track of time. And hopefully what we'll do is we'll have a little bit of a break at about 11 o'clock our time, which is in about an hour. And hopefully we'll get through sort of like the background of what reinforcement learning is about by then. And so the second hour will be possibly on a little bit more technical side, but also hopefully we'll get into the section that I've got down the bottom, which is talking about how to run gymnasium and how to make use of some building blocks that you can use that are available for free on the internet to start your reinforcement learning journey and really get into the possibilities that it can help with. Okay, so let's go and try and get an idea of what reinforcement learning is. And I just want to pose to you an example problem here. So this example problem is to do with controlling a helicopter. And in this case, key problem that you have with any helicopter, and if you're a helicopter pilot, you probably know this. If you're not, you may realize that actually being a helicopter pilot is a very a difficult skill to learn. And one of the reasons it's difficult is because there's sort of two things happening at once. There's the ordinary sort of problem that you have of, how much sort of forward do I want to be and how much up do I want to be, but also you need to be worried about the whole aircraft spinning. So how do you do that? Well, you have to compensate really all the time for the amount of torque being given out by the main rotor blade. As they spin around, the natural thing is for your aircraft to try and spin the other way. Even though the blades are relatively lightweight, there's still quite a bit of force going, and you have to compensate constantly for that. So as you increase the rotor blade speed, you also need to change the torque tail rotor. And this constant battle of compensation makes the job of being able to even do the basics of staying level and flying straight, slightly challenging. Okay, so you might wonder, okay, so we already have a difficult task to handle. Now imagine doing this for a model aircraft, so model helicopter. So the problem there is even greater because you're not actually physically in the aircraft, you're standing on the ground, which is probably a good thing from some points of view. But the point is that now you've got to sort of translate your head into the space of this aircraft and control it. So it's quite a challenging thing to do. Which makes this video all the more remarkable. Now, when you first look at this, you're probably saying, well, surely this is just completely out of control. But actually, this is a stunt. It's called chaos. Essentially, it's to swing the helicopter around in a particular way, and it's designed. It looks chaotic, but actually, it's designed to do particular things to the aircraft. Right, and that is being done by reinforcement learning. Now, your initial view of that might say, okay, well, that doesn't look that clever, right? It's not that smart to be able to get that aircraft to swing around. But in actual fact, there is a lot of things going on there, and I just wanted to pay attention to at least one thing: is that towards the end of the thing, you'll see that it comes out and is in perfect level flight. Right, so not only is it able to do this very chaotic thing, but it also is able to recover completely and get the aircraft stable again. And I think that at least is something that we should say, oh wow, that is quite amazing. So I'm just going to continue on. So let's just think about what reinforcement learning is for a second. So we have, in the terms of our overall paradigm of artificial intelligence, we break it down. We get inside there, we think about machine learning. Machine learning is essentially the art of, or the part of artificial intelligence that's to do with learning how to, getting the machine to learn how to do something in particular. And typically, a lot of it has been focused on what's called supervised machine learning. So, for example, being able to recognize, it's a famous example of a young computer scientist who saw his parents. They were trying to detect whether or not the cucumbers were the right shape and put them into a separate box if they were the wrong shape. And he automated this task. You've got a camera, it looks at the cucumbers, it says yes, they're right, or no, they're not. And through the process of supervised machine learning, he was able to devise an algorithm basically to learn which ones were the good ones, which ones were the bad ones, and be able to kick the bad ones into the right box. Okay, so now that is an example really of doing machine learning at the basic level. We can also have another area which is called unsupervised, which is essentially where we've got clusters of things. So we want to be able to say, okay, all of these things are all happening together. People individual customers are coming to a store and buying certain goods, but also buying certain other goods. And we can identify the link between, essentially the links between those two things happening. And that's useful information, for storeholders, for example. And the final one is reinforcement learning. We categorize it separately because it's got some separate sort of issues with it. And the main sort of character of reinforcement learning is it's about things to do with what are called sequential decision problems. So not only are you worried about what you're doing in the next step, but there's also consequences from many steps down the road. And an example might be a game of chess. So for example, you make a move with the pawn, and then if that's a poor move, that can have a consequence later on in the game. And similarly, you know, you might actually sacrifice that pawn because it has a positive consequence that's called a gambit, right? So being able to make an assessment of those sorts of things, you know, in sequential decision problem is a key element of what reinforcement learning can do. Okay, so let's just think about, we need to define some common language here. So the common language that we have for talking about reinforcement learning problems. The first one is what is, you know, how does the agent behave? And the thing that you need to know here is the term policy. What does policy mean? It means a mapping of situation to action. And actually, it's a mapping from every possible situation to the action that is appropriate in that case. Now, when I say appropriate, you could have a good policy or a bad policy. You might even have an optimal policy. But the point is that the term policy is basically about that mapping of situation to action, right? So, and then another term would be the reward function, right? So we need to define the outcome that we want in some way. So in terms of a game of chess, the reward function tells you about, for example, whether or not you win or lose. Sometimes there's a temptation here to define the reward function in terms of intermediate goals, such as, for example, whether or not you know, how many pieces and what the sort of value of those pieces. You know, you can say pawns are 1 and bishops are 3 and so forth, right? So you might think about a reward function that is worked out in terms of value. Now that can be a good approach sometimes, but because you are not actually now talking about the real goal, which is to win the game, but an artificial goal, then that can change what is actually optimal. So there sort of can be a negative sort of side effect of having these intermediate ideas of what is good value. And we can talk about that in a minute. Okay, so just assuming we've defined our reward function for a second in terms of the long-term goal, so you know, you win or lose the game, and say +1 is for winning and -1 is for losing, maybe 0 for a draw, then the value function is looking at each individual state of the game as it goes through and being able to assign a value associated with that state. It basically looked like a little prediction of whether or not we're likely to get to our positive goal or would we end up in a negative goal, right? So the value function is just a mapping from our current situation, our current state, to a value that is associated with what the long-run desirability is, basically how good that state's going to be. And if you wanted to think of this in terms of economics, you know, if you're investing money, you can think of it as the net present value, right? So it's basically saying, you know, you put in money into an investment, you know that that's going to earn interest over time, but you still consider that money yours. So your sort of net present value tells you, you know, what you're getting out, but in current day terms. Okay, and then final term that we need to define is the idea of a model. So this is basically how the environment responds to your actions. And in the case of a game like chess, this is sort of including the other player as well. So in other words, you move a piece and then sort of magically another piece moves to counter your move, right? So the model is the environment. Now, that's going to make maybe more sense to you in the case of something like a robot. You know, it's for example, it moves its leg, but that causes it to fall over, right? So the environment is the bit where it falls over, right? The environment tells it to say, this is how the sort of physical world reacts to that action of moving the leg. Okay, we also can talk about the idea that we need to think about a total set of possible states and actions. So within the idea of a model, we also need to think about, well, what are the total possible sets of states that are within that? And also, what actions are appropriate in each possible state? Okay, so I'm just going to pause this video for a sec, and we'll go through it step by step. Right, so we have an example problem here. Well, I've talked about chess and I've talked about robots walking, but I want to take a really simple example and just walk you through what's sort of going on a little bit in more detail. So it's to try and embed these ideas of policy and reward function and value, and we'll sort of explain how they actually pan out in this example problem. So the example problem here is a classic problem. Actually, you can find it in many classic books on artificial intelligence. So that basically it's a grid, what's called a grid world. And in this case, one of the squares of the grid world is blocked off. We can't go there at all. That's marked in white. And then another square is this one over to the right here, is marked as a -1, which means that it has an associated penalty to it. If you happen to go there, then that's the end of the episode, and also you lose effectively, so you get a -1 reward. If you manage to get up to the top right-hand corner, on the other hand, you get a +1 reward. So you can see it's a very simple game. The idea is for you to start, say, down the bottom left-hand side, or you could really start anywhere, it doesn't matter that much, and you want to eventually get down up to the +1 reward. Now, there is a slight complication here, which is, and this happens with lots of different physical environments as well, that we're going to define the action that you take as being a little bit sort of slippery. So in other words, that your environment reacts to you trying to take an action of, say, going north by sometimes taking you north, right? Sometimes it does. But 10% of the time, it will actually cause you to go off to either side. It will never take you backwards, but it will, sometimes it will take you to the right of where you asked to go, and sometimes it will take you to the left of where you asked to go. Okay, now you might say, well, is this really realistic? Does this actually happen in the real world? Well, this corresponds really to lots of real world problems because, for example, we have, if you have a car or a robot with wheels, then the wheels might slip. So you need to sort of account for the things that basically you can't see, you can't exactly measure or control exactly by introducing this little bit of probability over, you say you want to do something, but actually the outcome is not necessarily exactly what you asked for. Okay, so we've incorporated that. Now, if we just examine one particular state, so we're going to take the state where we say, okay, that one in the bottom left-hand side, and now we'll sort of expand it out, right? So we're going to firstly consider each possible action that you could take, and we've only got 4 actions that we can take. Here, we can go north, south, east, or west, and those are represented by the arrows out of the orange square, which is, our starting square. and a little dot. Now we also have, you know, target locations that we could get to that are nearby, right? So we might end up actually physically going north, or we might end up going east. There aren't any squares off to the west or the south, so we just leaving those unmarked for the moment. Okay, so we can annotate those probabilities. Remember how we said, okay, well, we got 80% chance of actually going north when we say to go north, and we've got a 10% chance of ending up going east, right, when we tried to go north, and a 10% chance of going west, but actually because we bump into a wall there, that just puts us back into the same location. So you can see that from our starting point, right, we tried to go a particular direction, but the outcome may be slightly different, okay? Right, and it turns out that we can then continue to annotate all the possible actions that we could take. So for each possible action, we look at what could happen as a result, and we just do these annotations, and then we can take this back and, you know, say, okay, let's start with working out our first initial view of what we're doing is saying, okay, let's have a default policy which is completely random, right? In other words, with equal probability, try going north, south, east, or west. I don't care, right? I don't have any information about what to do, so I'm just going to randomly go to any possible thing, right? Now, based on that little probability diagram that we worked out before, we can then use that to estimate, or to actually calculate exactly in this case, because it's a relatively small problem, the value, the long-term value of being in each individual state. So that's basically given the policy that we have, which is completely random, right? The long-term value of being in the start state is minus 1.547, right? Now you'll notice as we get closer to the actual goal, then we get a better probability, get better value estimates, like it goes down to minus 0.275. But overall, it's all negative. And you think, well, that's not very good. How do we end up with such a poor result? And that's really because we're just doing things randomly, and we can do much better than doing things randomly. Just move this to the top. Okay, and in fact, if we just take those numbers and we look at, you know, where could we go best? So, for example, if we look at our location here, over here in this top left-hand side, we could choose to go east, or we could choose to go south, right? But then if we actually look, the value that we gain, you know, on average, it's including all of those, you know, 0.8 probabilities and so forth, right? We'll actually do slightly better if we try and go east than if we go south. And we take into account, well, the possibility to go north and west, by the way, but the main thing is that we're going to get a different idea of what the good policy would be, right, based on this value. So we can update our value, and there we have it, right? We have an updated estimate of the best policy based on our previous set of values. Now, you might say, well, is that the solution? Is that all we need to do, right? Do we stop there? Well, no. And the simple reason you might realize that we don't want to stop there is you look at that and you realize it's not actually all that good. Take, for example, this state down the bottom, 4.1, right? This one is saying, well, just go straight into that hole. Well, you think, why would it do that? Well, based on the previous values that we had, that looked like the best move. But actually, it's not the best move, right? And why not? Well, it's not the best move anymore, because when we update the policy, the values are going to change too. So let's just see how they changed. right? So now we re-estimate the value and we look to see, now we're getting a positive value here, right? It's no longer negative 1 point something, it's actually going to be better than this, right? So now it's going to be clear from this point, we need to actually go this way. Okay, so we're now into the stage where we say, we've got an iterative algorithm. So we continue this process on and on and on. And eventually, we're going to work out when to stop. When do we stop? Well, we stop when our policy stops changing. So we keep going until we finally get to a policy that stabilizes. And you can see this is the final point where no more changes are going to happen to our policy, and that's our final point. Now, the thing to be aware of here is this does not, as it stands currently, guarantee that we won't fall into the hole, right? And in terms of how reinforcement learning works, right? That's an important thing to think about, because we want our results to be perfectly safe, don't we? But actually, we can never have perfect safety, right? That's never the case, right? But we could possibly have more safety than this. And it's a question of basically how we treat these, this negative 1 here. What we can do is just update the negative 1 and say, actually, we really, really don't want to be here, right? So we'll change it to a negative 10. And now let's see how the policy evolves from here. And we just continue playing and evolve the policy. Eventually, we'll see very quickly that the policy we get to, the final arrangement, is saying, it's so important to me not to go anywhere near this disastrous place that I'm actually just going to butt myself up against the wall until by chance I move off to a safer place. Okay? So this is how big this number needs to be, essentially, or how negative it needs to be before that starts to happen. I haven't actually done the experiment, but you can see the point is that as it gets larger, negative, then this definitely it'll change its behavior and change how it deals with the problem. Okay. Yeah, you had a question.
But even this wouldn't be the policy, optimal policy, because if the player is randomly spawned in the 1/4, that cell, bottom right corner, if it's spawned there, the policy states that it's gonna keep bumping against the south wall and stay in its space, because the negative 10 reward is so bad that it's gonna avoid that. So even this is not an optimal policy, because we're not eventually.
But it's got a small chance of, whenever it tries to go south, it's got a small chance of actually going east.
It's safer to go south than to go any other direction.
Yeah,
because of the slippery condition.
Essentially, it's to do with the fact that it's got a slippery output. If it didn't have the slippery output, if it didn't have any slipperiness, if it always went exactly, then you're right. This wouldn't be a very good policy. And it wouldn't have also needed to have done that to protect itself. So let's have a look at just a few other example problems. And now what we want to do is sort of embed in your brain, really, the idea of what a state is, what an action is, and what a reward is. So in this case, this is a pole which is hinged and sort of being balanced by a little cart which can move just left and right. Okay, you can't do anything else. But the way the hinge works, it doesn't need to do anything else. But it is dealing with a very highly dynamic problem here, right? It's going to be very easy for this pole to fall over, right? And by the way, the image that you're seeing here, that's being developed, obviously in simulation, but the starting policy would have been would have always been falling over. It would have always failed, and so it's learned how to keep this pole up by just doing these actions, and the actions that it's got to do are to move the cart left or right. It can, you know, that reinforcement learning agent has learned to, and it's learned on the basis of a reward function that says, keep the, you know, for every time step that you're keeping it upright, you get a +1 reward, right? Okay, and the sorts of things that you need to know to do that are the pole angle, the angular momentum, the cart position, and the velocity. And this whole set of 4 different variables forms a vector, and we call that like that vector as being the state. Now, it's worth pointing out at this point that up till this time, we've really dealt with states which were very definitely finite and very limited in number. You know, the previous example only had 12 states or 11 states or something like that. This has actually many more possible states. We might not want to deal with the pole angle a very fine number of degrees. So, you know, in principle, we can have a finite number. We can actually do it finitely, but there will be many thousands. So it's going to be seemingly infinite, right? So here's another problem. So this is to do with robots playing football. This is from 2019. I had a look at the 2024 videos, and I thought they weren't actually all that much more interesting. So I thought, you know, just keep with this older one. This is actually the middle-sized league. They're also sort of humanoid robots. But the important thing here is that the problem for playing football for any individual agent, and we call an agent in this case a single robot, is to work out, for example, they need to have an estimate of their state, and the state will be not just where they are, but where the ball is, and maybe even where the other players are. We also need to think about what actions. So the actions, again, could be in terms of the forces being applied to the different motors that we have. So, you know, the going forward motor, the going backward motor, the going left motor. Then you also might have like a kicker. So I think these robots, you'll notice they almost suck the ball in. What they're doing is actually rotating a little thing that sort of spins the ball backwards almost to keep it onto itself. And then the reward function, again, this is very much like chess. You want 1 for a win, 0 for a draw, or -1 for a loss. You could have a soccer playing robot, a football playing robot, be working out what to do on the basis of the score, right? So in other words, you know, that it considers a score of 8-0 better than a score of 7-0. But, you know, some also would argue that actually it makes no difference to have 7-0 or 8-0. So, you know, once you've got a decent score, maybe you can just concentrate on defending, right? So, and in actual fact, real soccer teams will play that way. They'll actually be focused more on winning rather than just scoring points. Okay, so where does the idea of reinforcement learning come from? So the earliest work on this is really to do with Pavlov's dog. Of course, Pavlov's dog is a little bit icky to think about, so I think much more fun to think about cats. And this really gives the idea that reinforcement learning is something that really is embedded into both animal behavior and human behavior. It's something that we sort of come to accept as being an important part of how we learn stuff. And particularly, how we learn to act to gain the things that make us happy, right? And actually, you could think of happiness actually as being sort of super important. It's a super part of the whole reinforcement learning infrastructure. Happiness is your reward function. Okay, so very early work, of course, was to say, now, if we've got these ideas about how robots could work, you know, that could be based on some sort of reinforcement learning. And sort of very early mechanisms were to get a basic robot to follow a light and to steer towards a light. And this was early work by a colleague of Weiner. And then subsequently, we had sort of more theoretical underpinnings about basic decision theory. And Richard Bellman came up with this wonderful equation, which is briefly summarized there. So I'll just play that again so I can explain it a little bit better. It's saying that we have our rewards that happen at different times, and they're discounted, right? So we get less. It's less valuable for us to get something in the future than it is to get it now. If I say I'm going to give you £10 tomorrow or £10 today, which would you choose? You say £10 today. Thank you very much. I want the £10 now. So you might say, well, if I gave you £11 tomorrow, would you accept it? So, oh yeah, that's great. I'll have the £11 tomorrow. So exactly working out what your real sort of discount value is, that's quite an interesting question, right? So economists will argue about what gamma should be, but basically it's going to be corresponding to, how valuable things in the future are versus how valuable it is to get the same thing now.
So basically either prioritizing a long-term reward or an immediate reward, right?
Yeah. Okay, so the next thing that was happening in reinforcement learning was that people were starting to experiment again with just not necessarily having a firm or fixed idea about how either robots or even computer programs could learn how to do something, learn how to take action, right? So they're just experimenting about it, and they came up with this idea of the temporal difference error, which is basically the difference between what you thought you were going to get and what you actually got, right? It's essentially an error signal to say, well, I thought I was going to get this, and I did, and that's great. Or I thought we're going to get this, and I actually got much less, so I should downgrade my expectations in future. Or I actually got much more, in which I increase my expectations, right? So that sort of feedback loop is a critical idea, and it was really just experimental, just a hack essentially, not necessarily saying this is exactly how humans work, but this sort of corresponded to what we thought and seems like a right idea. So having done that, this was really surprising, right? To say there's a link actually between this formal decision theory idea of Bellman's equation, and it took that back and made it do almost exactly the same thing with an update equation that is looking again at what I said was temporal difference, right? Basically the difference between what you thought you were going to get and what you actually got, right? So in this case, the thing that you thought you were going to get is represented by this middle section here. This saying the action that was going to maximize my value here, and what you actually got was this reward that you actually received. Okay, so that was really successful. It's a very fundamental algorithm in AI or in reinforcement learning. It's called Q-learning. So far, it all seems really theoretical, but then someone came up with, Tesaro, I should say, came up with this game player, backgammon game player. And this was surprising in two ways. Firstly, this was one of the first algorithms to make use of neural networks in the back end, right? The second thing that was really surprising about it was that it was actually so incredibly good at doing its job that backgammon players learned how to play the game of backgammon better, right? So there's a little bit of detail here about exactly the situation that occurred. And they said, oh, wow, we hadn't thought of ever doing that. So yeah, this is a nice example about not only a superhuman playing of backgammon, but also something that showed a difference in how to play the game. Similarly, in neuroscience, what was interesting here was that the neuroscientists started making models, mathematical models of how the dopamine signal works. And they realized that there was a correspondence with this idea of the temporal difference algorithm. So basically saying that the reinforcement learning mechanism that is going on in, that we're currently thinking about in robots, well, actually corresponds pretty much to what we're seeing in the dopamine reward signal. Okay, so this is an ancient work from me. I did this in the year 2000, so over 25 years ago, and to basically build one of those soccer robots. Before we were sort of clever enough to make them firstly be able to move in all directions and also be able to see in all directions. That's one of the key characteristics of those modern robots. Right, but nevertheless, fundamental issue with just getting this robot to move to a particular target point. Now, you have to deal with a cart that has sort of two wheels. To get it to move to a target point is actually slightly complicated. It's not an obvious thing. So in particular, if you start off with some momentum, you can see this robot is starting off at the red point here, right? When it actually starts to say, okay, well, now I've got to move to this green circle over here, but instead of being able to do that immediately, it will first have to slow down and stop and then turn. And when it turns, sometimes it will turn too far. You can see it's actually swung all the way around and its momentum carried it around way too far. And then it said, okay, well, now I've caught up and I need to turn backwards, right? And part of this is just the things that are happening in terms of inertia, and part of it is the latency associated with the sensors. But these problems are difficult to work out when you're writing code to do this, right? It's actually, I suppose, one of the things that I'd like to point out, it's probably not impossible to write better code than this to get a robot to move to a target point. But it becomes extremely complicated to accurately take care of all these little details to do with the existing momentum of the robot, for example. Now, I should point out that this is actually a data trace from a real robot. So even though it's shown as a graphic, there was a real robot trying to do this maneuver. And actually, it's the real robot that causes a lot of the problems because all of the extra things like latency and so forth are happening with real robots that don't necessarily occur in simulation. So that makes this was really surprising to me when I was doing my PhD thesis. And this is actually very close. I was able to show this was very close to the optimal set of actions to do. And as I said, it's a real robot that's doing it. So it was so much more efficient than the hand-coded version. I also looked at another problem, which was to do with dribbling the ball, and you need to get the ball from some part of the field, and you want to scoop it up, but also guide it to a target point. So how do you do this? Well, my hand-coded version was managing to sort of scoop the ball a little bit at the start, but it became very easy for the ball's momentum to sort of shift it out of the grippers, and it sort of floated off to somewhere else. But as I said, this was the version that I had done by hand. You'll see the robot is moving in a really nice straight line, which is what you tend to do when you're coding by hand. You don't think of doing anything else. And this is what happens when the reinforcement learning algorithm attempted to do the same thing. It's not perfect, right? It's not actually doing a completely perfect job. You'll see that ball is sort of bubbling out from the grippers a little bit. We hadn't thought of having those nice reversing motors to keep the ball close at that stage. But you'll see that it's much more organic movement, right? So it's taking care of this, the little movements that it's seeing in the ball, It thinks of the velocity of the ball, not just the ball's position, which is difficult to take into account when you're coding. Okay, so let's just go back to that helicopter, and just now we've sort of understood a little bit more about what reinforcement learning is. We can sort of come at this and appreciate it a little bit more, right? So this is a series of stunts being flown by an autonomous helicopter. It's not being controlled from the ground. They're taking it through a series of target maneuvers. Each one of those would be challenging for a human operator. Although you can't really see it on the screen, it might be even more difficult over Zoom. I'm not too sure if people are having difficulty seeing it over Zoom. But you can see that things like being able to fly backwards, do sideways flips, fly inverted. These are really challenging things to individually to do. It can string the whole series of them together, do them flawlessly, and maintain the helicopter's altitude, right? So quite stunning sort of victory. This was in 2004, right? And you think, well, why have we not progressed further, right? So this is probably the first question you're going to have. How do we get stuck here? How do we not progress very early on? And the reason that we didn't progress very early on was, and the thing that made it really hard, was being able to incorporate the wins that we had from neural networks into reinforcement learning. It's a fundamental problem that needed to be unstuck. Okay, and when it was unstuck, everything changed, right? And the key thing that unstuck it was 2016, the development of an algorithm called DQN, which was basically deep Q networks, a mechanism for combining in neural networks and Q learning, and to do it successfully. So you might be saying, okay, well, why was this so amazing? Well, one of the things to point out here is that this, the input to the agent, the reinforcement learning agent, is not the underlying internal values in the computer game, right? It doesn't have access to that. What does it have access to? It actually only sees the pixels on the screen, just like a normal human player, right? And suddenly you start to realize how challenging this problem is. It's got to be able to correctly interpret that and work out, whether or not to move left or right. It actually needs to be able to see its own paddle on the screen. It doesn't have a record of where it is. So they actually were giving it a series of frames, not just the last frame, but a series of frames so it could work out what was going on. Okay. And about this time, we also had a really big advance in developing, so sort of like a sort of subsequent advance that was the development of AlphaGo. And the reason why this is so amazing is that it combines, that basic sort of idea of you being able to do these deep neural networks with, a number of other technologies that were coming around, ideas that were floating around at the time, and to show how powerful they really were, right? The actual computer that ran the final version of AlphaGo to beat Lee Sedol, and by the way, if you haven't heard of AlphaGo, I really recommend you go off immediately to YouTube, after this lecture, and watch the video that you can find there. It's a really fascinating story. But the point about it is that they're able to do all of this, and because it's reinforcement learning, because you've sort of worked out this, through lots of trials of self-learning how to play this game, and now you have a policy, you have a way of mapping from the situation you've got to what you do, which meant the AlphaGo ran on a laptop, right? Did not require, as they did with Deep Blue, this huge arrays of mainframes hooked up by Atlantic cable or whatever. It didn't require that. Why not? Because essentially what reinforcement learning essentially does is learns the policy, and the policy can be expressed relatively simply. So, powerful idea, really. Okay, so that's still playing in a simulated world. What about we try and take it outside a simulated world and apply it to real physical objects? So the starting point here was to try and learn how to get this gate to work on a real robot. And you can see that the first try failed really badly. And then they went back and improved the simulation, and they were able to get it to be closer. Now, this problem generally of the simulation not matching up with reality is called the sim to real gap. And it's really important because it's a sort of identifying that whenever we do go from a simulated problem to a real problem, we need to think about and take care of the fact that the simulation may not be perfectly matched to the physical world. Okay, so I'm just going to continue. So the next key advance was to work out how do we really close this gap in general, right? And this was the first sort of real breakthrough in a way. I have to say, in addition to being a breakthrough, it was also a disastrous failure. Like the OpenAI cancelled this project after investing huge sums of money in getting it to work. So just to tell you what's going on here, what this is a robot hand that's being able to single-handedly manipulate a Rubik's Cube. We all know that single-handed manipulation of Rubik's Cube is a dexterous task. It's complicated enough, right? And you can see it's sort of having a little bit of trouble here. And the reason why it's difficult is because ordinary Rubik's Cubes have a stick-slip point, right? They're going to stick at some points and slip at other points, right? And you can't tell until you try it whether or not it will stick or slip, right? So the problem is, of course, translating the sort of really tricky bit of physics into a simulation is really difficult, apart from anything. Even if you do it successfully for one particular example, then when you come and try and do it again, then actually it won't work because something different's going on. So what they did here was that they made a simulation that would do lots of different ways of the sticking and the slipping happening. And then they trained it with all of those different variants. And that's how they got this thing to work. Oh, I've done the wrong thing. Sorry.
You said they cancelled it, suggesting they didn't get it to work.
They cancelled it after getting that far. They didn't take it any further. Okay, so let's see if we can get our videos to run. So this is another example of getting robots to work in the real world. Now, the experiment here is slightly different. So instead of working purely in simulation, what if you could learn in the physical world? Now, the trick that they're trying here is to use a process called dreaming. Essentially, it's saying, rather than create a simulator, first simulate loads of times and then transfer that to the robot, why don't we have the experience of trying to move, use that experience to create sort of like an idea in our head of how physics works, and use that dreaming process, simulate try out in our head, or in the robot's head, doing particular actions until we find ones that work. And what this means is that something that ordinarily would have taken far too long to learn in the physical world, for, you know, the robot would have probably been broken, and the PhD students would have been long dead before the robot learned anything useful. So to get it to be faster, essentially, we need to do some computation in sort of like in our head, in the robot's head, effectively, but as well support that with the thing. Now, what I wanted to point out with this video, if I can just get it to rerun. Do that. So when you start seeing it being pushed over, I think the walking gait is not particularly good. But look particularly how well it behaves in terms of getting up, right? It's pretty amazing about, you know, recovering. It seems to be able to recover from almost any position. So this is the thing that you'll find actually, if you think about it, a lot of its learning process has happened, you know, basically falling. So it's experienced a lot of this really early on, and because it's experienced it, it knows how to do it really well. Okay, I can't help but show you this one. I think it's a fabulous bit of work. There's a number of really key aspects to it. I'm just going to place a brief section of it from about here. So this is showing that we have what it's basically doing. It's learning in simulation how to fly a drone through these hoops. And you'll see that, you know, at the very start, when it tries it, let's just go back a bit. So its initial, initially, you know, the drones are just going all over the place. And gradually, it's learning through that reward signal to get better and better at actually flying through the hoop in the right direction, right? And then you get to a point where it's completely and utterly able to fly really reliably from a variety of different positions. So even if it gets slightly off course due to sort of some variations in the physics, it doesn't matter, right? Now, I don't know if this is playing full speed on your video, but it is amazingly fast when you see this play, and I highly recommend getting access to finding this video online and playing it all the way through, because it's a really fascinating discussion of the problem. Okay, so you may have also heard of the use of reinforcement learning to do with ChatGPT, right? And this is an algorithm called RL with human feedback, reinforced, or RLHF. And it's a key enabler, right? Because we wouldn't have had ChatGPT being able to be out in the open unless we had something like this. So how does it work, right? What's going on with RLHF? Essentially, the point about RLHF is that it's to align the large language model with human preferences, to have the 3 H's, as it were, the helpful, honest, and harmless characteristics. So the first step is to train a model of the behavior of the reward. So in other words, we don't actually have a reward signal. There's no right answer to a chat conversation, right? Nobody can say, well, this was an exactly perfect chat situation. And certainly we can't do that automatically. We might be able to get a human to come along and annotate and say, this was an okay response, or this was not an okay response, or even to assign preferences to say, this one is better than that one, okay? And given that they can assign preferences, you might say, well, maybe that's a basis for deriving some sort of model of what those preferences look like, right? So that's exactly what they did, right? They said, let's get 40 annotators. And then they got another set of 40 that they didn't carefully curate. And they combined those people and said, now go and try out ChatGPT without any guardrails or anything like that, but get that to respond to you. And then when it responds, you're going to get two options. One is going to be option A, one will be option B. Tell us which one you prefer, right? Okay, and through that process, they got lots of annotations, probably tens of thousands of annotations, right? But that's not enough, right? It's a relatively small set of examples to learn from. How do we learn from that? So the way that they learned from it was by using that as a training set to derive a reward model, right? From the reward model, that was used then to use an algorithm called PPO, which is a reinforcement learning algorithm, to train on a much larger set of examples. So in other words, to automatically provide the preference feedback to this huge, not just 10,000, but more like 10 billion examples. If we had to do that job with humans, it would have cost more than we were able to, many more billions, and also much more time. It would have been, even as it was an exhaustively long-winded process. Okay, so that problem of having to deal with humans sort of modeling made the people developing DeepSeek realize maybe we could do something that gets us past having this proxy reward model, right? So the problem with being the proxy is that it's not grounded. To give you an example, if you ask ChatGPT for a recipe, right, you might have a human being able to say, well, this is a good recipe or that's a good recipe, right? And when you have a reward model, they're really just thinking about, you know, does it sort of vaguely look like a good recipe? Does it sort of it's not exact, right? So no longer do you even have the exactness of a human judging it. You certainly don't have the exactness of a human actually baking the cake and tasting it, right? So if we were able to bake the cake and taste it, that would be considered grounded feedback, right? Completely and utterly, you know, the cake, we know that the consequences of the cake, you know, maybe even the CO2 footprint of the cake were on the positive side, right? So with some problems, however, we can get grounded feedback. So in the case we have of here, for either mathematics, so maths problems, or for code that you can write and you can test, then you can actually have this grounded feedback. So we can get, really, we can reward on whether or not the answer is correct, not just whether or not it's compliant with the norms. So it does leave a sort of open question here about if we could do grounded rewards for other sorts of large language model conversations. And this is brought up by a recent talk by David Silver, and he's got a paper, a position paper called The Year of Experience that picks this up. And this is actually from The Year of Experience. So he's really saying, you know, with things like alpha proof, we're starting to actually get to a stage where we can think about algorithms that basically can learn from, can self-learn and really go past what humans can do. You know, we can't really go past what humans can do with just sort of vaguely knowing their preferences. That's never going to go past. So to be able to think about the consequences, the long-term consequences of things, that's where we're going to be able to really change things up. So way over time for my first hour, so I'm going to let you have a quick break And while you're breaking, we can just watch another little video, which is some robots doing some walking. And please do have a sip of your coffee, tea, other beverage, and relax for a few seconds while we take a break.
I have one of these dogs over in the engineering building.
Do they do this with it?
I've not seen him doing that, but I was there working late one night. It was about 7 or 8 PM, and then the dog just walked past my office. I don't think anyone was controlling it. I don't think anyone else was there. I just think it had decided to take itself out in the evening after everyone had gone out. That's what it seemed like. It's bizarre.
Yeah.
There must have been someone there somewhere.
So maybe a security dog. Right, so we'll quickly come back and continue on, and I just wanted to last thing to talk about how one thing that's fascinating to me is that whenever you see a diagram of the way the growth of reinforcement learning goes, then you get sort of this sort of graph. Now, the interesting thing to me is that I was studying back to my PhD back in 2002, and you know, we were looking at this same sort of graph, right? It's just that because the y-axis has changed, you know, down in this early part, it still looks pretty dramatic. So what was going on even to 2015? You know, massive increase in research in reinforcement learning, but there's in no doubt that it is really taking off. And I didn't include 2025. Which may seem strange to you, but anyone have a guess of why I didn't include 2025?
Because the year hasn't ended yet.
It hasn't ended yet, and it would make the graph drop away, and you'd think, well, what's going on with reinforcement learning? No, it's just every predictor would be that it's going to be way up there. So far this year, there's still a ton of research papers out there, even this year, and it's going to continue. Okay, so there's an old adage that says that the first part of the lecture is for everybody. The second part of the lecture is you know, for a very select few, and then the last person basically last part is for the lecturer. So unfortunately, I'm going to get to the last part very quickly, which is to tell you really the basics of how this stuff works. And the reason why I decided to do this, rather than say focus on you know, maybe doing, we'll have a little bit a section on the practicalities towards the end, but the reason why I've tended to focus on this is because what I have found is that if we don't discuss these fundamentals in excessive amounts of detail sometimes, then it's easy for you to think, well, this is all too complicated, somebody else can think about it, I'm not going to worry, right? We've actually need to help you through understanding all of these basics, primarily because, not because they're complicated, but primarily because they will help you understand the bigger things later that come along, okay? So get these, so let's just go through these basics, and even though they are going to seem like, oh, it's maths, I think it's still worth just going through. And hopefully I can explain the maths to you a bit. Okay, so this is the starting point we have for a fundamental mathematical construct called the Markov Decision Process. And essentially what that is it's a process that involves a combination of two entities, an agent and an associated environment. And the agent is acting in the environment. It acts by any particular time step, sending in an action signal AT, right? And it receives back the state signal from the next time step and a reward signal at the next time step. So we get this feedback loop. It's a relatively straightforward thing. Probably the first thing to note is that everything is happening in regular time steps, right? And those regular time steps make you end up with this sort of sequence. You have a state that you start in, S0, an action that happens next, that's the first action you take. And obviously you can't take an action without knowing even the basic of where you are to start off with. And then you get as feedback a reward signal and the next state. And then you're off again. You say, okay, well, now I'm in this next state, I'll take a new action. And when I say I'm in the agent. And I get back from the environment a reward signal and state. Okay, and so forth. So we can represent this using a sort of formulation, diagrammatic form called a backup diagram. Right? And what is happening here? Well, the first thing, the top node of our tree is representing that starting state, or it could be any state really in our sequence, because really the same thing is going on wherever we are, right? And we are choosing from a number of possible actions. And the choice is dictated by a thing that we call pi, right? Pi for P stands for policy. It's basically our mapping from state to action, okay? So once we've chosen an action, we then will go from our little black dot through to the environment will send us through to a resulting white node, okay? So how does it do this? It does this on the basis of a transition probability denoted by P, okay? And we get a reward out and we also get a new state, okay? So that's our backup diagram in simply. So we have some terms associated with that. We generally say that the definition of a Markov decision process is this set of sets. We need a set of states, a set of actions, the rewards, it's actually a reward mapping, and the mapping, the probability model P for the environment, is called a transition model, and also a discount factor. The discount factor is just a real number, which is basically, you know, that tells us how we value future rewards versus current rewards. Okay, so let's just go over states for a second. So you could, in a Markov decision process, represent your state with a single number, right? You can also represent it as a vector of numbers, but ultimately you can enumerate them, right? There's going to be a finite number of different states, so you can enumerate them. So whether or not, how you exactly represent it is sort of up to you, but just keep in mind that for a Markov decision process, which has finite number of states, it's sort of like a mathematical definition, then you must be able to enumerate them. Now, a state should be a compact representation of all history, right? What I mean by compact is that it contains enough information to help you decide correctly what to do. An example would be, say, for example, you're walking through a maze, you might think that it's enough to know that your position in the maze. But actually, you might behave differently depending on your state of hunger, right? So you start I'll break into a run because I'm really starving now and I need to get through this maze, right? So your behavior, therefore, is going to change, right? And what the correct answer is, what the optimal thing to do is, might change as well. So you need to sort of somehow incorporate your hunger feeling into your representation of your state, So now, if you could do better knowing the history, right? If you basically, if knowing that you'd been in the maze for a long period of time was enough to sort of allow you to imply whether or not you're hungry, right? Then, you know, the state is does not have the Markov properties. This is a key property for a Markov decision process. By definition, they have to have the Markov property, right? So, in other words, if knowing the history helps you out, then we don't have our state does not have the Markov property, right? Now that can mean that we can sort of incorporate a little bit of the history into the state, and that's usually enough, right? So it doesn't necessarily mean you can't deal with that problem. It just means you need to change how you define what the state is. So we're going to come to infinite or continuous states later. So that's going to be another thing that we'll leave till later. And possibly really for another day, because we're going to run out of time. So we're going to have actions. Again, continuous actions are possible in various forms of algorithms, but we're just going to stick to finite actions because that's what a Markov decision process is defined as. And, you know, at each time step, we're going to take an action, but just keep in mind that that action could be a no-op. We might just do nothing, right? So consider the cart pole that was sort of varying where it goes, right? It doesn't actually have to force the cart left or force the cart right. It can do nothing. It can say, well, just don't apply any force. Okay, now whether or not that's true, of course, depends on your formulation, right? So the set of possible actions is sort of up to how you formulate the problem. Now, what happens when you take an action is going to be dependent on the environment, or in particularly in terms of a Markov decision process, it's dependent on this transition model. So basically a probability mapping from your current state in action to that next state and its reward. So this is what we're getting to, right? So the transition model. Now it's stochastic, right? So it doesn't mean that you always get to the same next state, right? So if you're in your starting state and you take a particular action, you may not always get there, right? We'll see an example of this later on. But fundamentally, the transition model is a representation of how the environment works. And this is actually a very general sort of approach, right? You can use this for lots of different systems. Talking of using this for different systems, it's a useful thing to know this sort of conjecture, I suppose. If reinforcement learning was to have a conjecture, then this would be it. It's usually called the reward hypothesis. And essentially it says that all the things that we've traditionally thought of as goals and maybe even purposes, we can actually translate into some form of reward mechanism, right? A maximization of the expected value of all the cumulative sums, they're basically adding up over time, of the received scalar signal, a reward. Okay, so in other words, it's trying to say that reinforcement learning is really a general way of thinking about pretty much everything that we do. Okay, so I now need to just come back and think about what's that value function, that reward that, that we want to look at. Not just our immediate reward, but what we're going to have in the long term, right? And we can represent this by our expected reward, which is G, right? And then G is defined to be, for say a particular episode ending at time T, capital T rather, then we have our rewards all the way up to the end point, right? Now, one thing to note here is that the expected reward at time t, right? This is this lowercase t here, right? Is incorporating all the subsequent rewards, everything we're getting subsequently. It's not taking into account what we've got already. You know, if we've earned some money, we put it in the bank. That's great. But like, you know, it's talking about how much interest we're going to get in the future, right? So it's just talking about subsequent rewards. Okay. So naturally, getting reward tomorrow, not as good as getting it today. So a discount mechanism is quite natural. Now, you can either have this first one, which is sort of not discounted, is saying everything is equal, or you could potentially have a discounted model, right? And you might be saying, well, which one do I choose? I don't quite know. You know, maybe sometimes I would want it one way, sometimes I want it a different way. One thing that you have a problem with this this first one is that if we have an infinite t, an infinite horizon, then we'd end up with infinite long-term rewards, which is mathematically not very nice. So we're going to try and avoid that. How do we avoid that? We either have to say we have a non-infinite t, or we need to use discounted, right? So we can unify these two ways of thinking about them in one stroke, right? Basically saying that they all pretty much look the same, but if we have gamma equal to 1, then it's going to be just like we had before, which is that but we have to restrict to a limited finite horizon in that case, right? So we can either have an infinite horizon or gamma equals 1, but we can't have both. Right? Now, the other thing that we can do here is that if we want to deal with tasks which have a definite episodic end to them, but we want to deal with them with the maths that we're doing, which is sort of say, okay, well, we have an infinite horizon. What we do is we have an absorbing state. An absorbing state, basically a little trap. It's like a little black hole at the end of the process. So that as soon as they get to that black hole, they get sucked in, and then they can't be seen anymore, right? They stay there. They can't get out, right? So that's the end point, right? You can think of it as a little black hole that you get into, and that makes it completely equivalent to an episodic form. And the nice part about this is that we're dealing with these two different ways of thinking about the problem, but we're doing it with the same maths. Okay. Policies. What are policies? Policies are essentially this idea where we have a mapping from states to actions, but we actually express them in a probability distribution. You might say, well, why do we do that? Well, that seems a really strange thing to do. We have a very simple thing. You plug in an S and you get a no. Isn't that simple? Well, yes, you could do that, but what we generally want to do is to have some level of randomness inserted in there. And that's really for exploration, right? So when we actually come to do this, we generally speaking will have what are called stochastic policies. Policies which have a, you know, maybe they're focused on, you know, pretty much we're going to take a particular action, but then with small probability we'll just take a random action. Okay, so we represent that as this probability distribution form, right, with pi a given s, and we say this translates to a number between 0 and 1, okay? And we want it such that it works like a probability, basically, that you sum over all possible a's and you'll end up with 1. Okay, so what are we doing for time? Okay. We probably won't get through all the material. So what I might do is once we get through the basics of Markov decision processes, I'm going to skip over it, just show you a little bit of gymnasium and then we're going to stop there. Okay, so for the value functions, we need to say, how do we know what number to put to say is the value of this state, a long-term value, right? We represented that previously by G, right? So the G was an example, right? In general, we may go through our state space in a number of different ways, even with the same policy, right? And what that means is that we need to actually average over these different trajectories that we've got through our state space. And the value is essentially our average. It's basically our expected value, and it takes into account that we're operating under pi. So it's important to note that we consider value with respect to policy, right? If you change the policy, the value will change, okay? We can also think of this other way, which is to say, what about the value of taking a particular action when being in a state? How valuable is it there, right? And we can calculate this, which is represented by Q, and particularly again, we're denoting it with the pi, which means that it's specific to that policy. So given that particular policy, then we will get expected value. And it sort of looks the same, except what we're doing here is, instead of just saying, well, we're starting in this state and not saying anything else, we're starting in this state and taking a particular action, right? Okay, so when we are in a particular state, how do we select an action, right? So we have action 1, action 2, action 3. How are we going to select it? Well, we're going to take each particular action with this probability, right? So it's basically saying we're going to select which action is based on that probability distribution. And that means that we won't necessarily always select the same action. We might say preferentially select A. It's A1, sorry. But sometimes we might also select A2 or A3, right? And note that we have a value associated with being in a state, but also a value associated with being in a state and taking a particular action. So the V is associated with this node here, whereas the Q is associated with this node here, right? So you might have different Qs for the different black dots. So once we've taken an action, right, what happens next, right? So the next is that there's a consequence. So you'll notice that now our top node is a black dot rather than being, if we just go back a slide, notice that was starting from a white dot, which is a state. Now we're starting from a black dot, which is we're at a particular action, right? Now the point is that when you take an action, the real world could respond in a number of different ways. And that's according to probability distribution, right? That's the transition model that says that, right? And I think it's important to note that even though lots of systems will behave very deterministically, we often going to make use of this idea that the environment is going to be stochastic. It's going to do something different, even though you're in a particular state and you take the same action, it might do something different each time. I think the other thing is that you might get different rewards out of it, right? The reward is often dependent on where you end up. If you end up in a goal state and you've actually got to the right point, that's great, but sometimes you slipped off the edge and you've fallen down the cliff and it's a disaster. You're lying in a heap with blood all over you, right? So in these cases, right, your reward might be, hugely negative, saying, it's a disaster. Right, so we can compare the Q value associated, the state action value associated with being here in this black dot to what the environment throws at us, right? It throws at us falling down the cliff sometimes, right? So this will be somewhat like an average of all of these, an average that is weighted according to the probability with which that happens, right? So it's only a very small chance that you actually end up falling down the cliff. That's associated, that the weighting will be small associated with that negative reward. Okay, so the next states, S-3, will also have a value associated with them. Notice that there's got the S prime here. That's basically saying this is the next state, not the state that we're in. Okay, so now we can think about optimality, right? So given some Markov decision process, what's the best value we can get, right? You know, this is like, you know, how do we maximize our happiness as human beings, essentially, or how do we maximize, you know, the amount of money that we have as effective, you know, in our bank from time point to time point. And so we are trying to maximize here by varying pi. So we're varying the whole policy. Now you notice policies, it's a complex entity, it's got lots of dimensions to it. There's, for each individual state, there's a different possible action. In fact, there may be a weighting according to probability distribution over actions, right? So it's quite, you know, we can vary this. This is quite a lot of things to choose. It turns out actually just a deterministic mapping for the policy would be enough to give us we don't need to have a stochastic policy for it to be optimal. A deterministic one will be good enough, right? So that's an important thing to know. But even so, it's a complex thing. We're changing lots of different things. And it turns out that if we can maximize any individual one for a Markov decision process, maximize any individual one, right? Then you can work that through as a basis for you know, improving anything else. So in other words, if you say, oh, I can just improve this little bit of the policy, just a little bit, and it gives me some better values overall, then that is a better policy, right? Immediately you've said, okay, well, I can compare two policies and say, if it's better in this particular point, then that's enough for it to make it better overall. And because you can keep maximizing and maximizing, keep improving, right? So then you can then say, well, there must be a maximal policy that gives us the optimal value. Okay, so we can also think of this in terms of optimizing the state action values. And this was sort of the basis for Q-learning, right? So if we come back to that thing we mentioned, you know, 1989, Watkins had this idea about connecting these two things. And this is really the basis of it. It's basically saying that we can instead of worry necessarily about the value, we can look at trying to maximize the state action value. And that also will happen when we have the optimal policy. So I'm not going to do this example, but these slides will be available, and what I'll do is I'll put a link into the chat to make it accessible, but you'll be able to have a go at these exercises later on and access the slides. Okay, let me just see how I'm doing for time. So to leave time for questions, I'm going to skip a little bit and just focus now on how we get practical, right? So you've got the theoretical basis for the Markov decision process, and now you say, okay, well, I want to start with doing some experiments just to see if I can understand a little bit about how these things work. So what we're going to do is basically start by grabbing, say, a Google Colab notebook and running pip install Gymnasium. And I think I have one that I can switch to here. It's down to the bottom. Right, so let's get it a bit bigger. So this is our first step, right? We're basically going to do a pip install gymnasium, and what that does is it brings in the base packages that we need for gymnasium. Now, I just make a note that this is just dealing with the environment part. What we're not dealing with yet is the reinforcement learning algorithms to learn how to deal with this environment yet. So we'll get to those hopefully, assuming we have time, but should be quite straightforward. Now, the next step after we've got an environment running, a gymnasium installed, then we need to do these couple of steps. So firstly, to do a Python import of the gymnasium. And in particular, we say as gym, you might be wondering about why we do this. Well, the original version of gym was produced by OpenAI and they stopped supporting it. So then the community said, no, well, we don't want this to die a death. And actually, we still want to make changes to it. They came up with a new version, they call it Gymnasium. But to keep all the documentation and all the examples pretty much the same, they generally import it as gym so that you can use the same instructions. And pretty much the interface is the same, but with a few minor tweaks here and there. So then the next thing we need to do is to create an environment. Now, there are some pre-made environments that we can play with. Some of these are called what are called toy text environments, which is sort of the most simplest thing. And essentially things like our example from before, which was a slippery place that has some places we can't go and some holes. That corresponds really well to what's called frozen lake, right? Essentially a lake of ice, but with some holes in it, and we can do that. Just see if I can run this. Assuming it can still run, it might take a while for it to do initialization. Okay, that's run. And now I want to create an environment. So if I just run that cell, I think it's going to run pretty quickly. And I can print off what's called a rendered version of the environment. Now, this little square of text is corresponding to our slippery lake. So we have our start position denoted S, and that actually is marked with a red as well. And that means that that's where we are currently. And we also have F corresponding to a bit of frozen lake, and H corresponding to a hole, and G corresponding to our goal, right? This is going to be our pot of gold at the end. Okay, so now we can set A to be, and A is going to be a number. So we can set it to, say, for example, 2, which means go left. Okay, and then in addition, we can ask it to create, I'm going to have to flip to my notes here. We'll just go back to the slides. We can ask it to go and do a single step on our journey, right? So basically ask it to interact with the environment. I'm going to choose action A, and let's see what happens. So I need to remember all this. I need S reward, terminated, truncated info. Okay. Okay, and we're getting it to fill it in here. It's going to be equal to env, and this is in the way, env.step. I don't know why that doesn't autocomplete, but So there we go. So basically what it's showing now is that we tried to go to the right, which was action 2, and we were successful at going right, okay? So now if we try and go action 2 again, I think that's, I'll just take a copy of this and create a new cell. And it actually has gone nowhere. So interesting enough, it's not done anything. So we'll just do that again. Now, as you do this experiment, keep in mind that the environment is slippery. And so sometimes your action will not do exactly what you asked. So for example, in that case, it might have tried to go north and bumped into the wall and then it ended up in the same position. So in this case, it actually did go right and it moved along. So now we've got a problem, right? If we go south, we end up between 2 holes and hopefully that will still work. So we can very carefully creep south and so forth. So I recommend doing the experiment yourself and trying this out and making sure that you understand what's going on. And in particular, you might be interested to try and print out the different variables we have here. So for example, if we look at, so if we just say reward, and it will output that for us. The reward was 0. What about terminated? That's going to be false. Truncated and will be false as well. So info, however, should be a dictionary of values. So it's going to tell us things like, you know, here it's telling us probability is 0.33, which I think is to do with the slippiness probability. If you want more detail, you really need to go to the manual. And if I just go back to my slides for a second, full screen. There is some documentation here, so we can go to that documentation. And it explains things like which actions go where, and also, you know, what the information is of transition probability for the state. So, for example, I've lost it. Oh yeah, I know why. Okay, so where do we take this from here? Why do I have that on my screen? No. Is that better? Okay, apologies for showing you my emails. So where do we go from here? So we can now do a number of things. We can generate a manual policy to try and solve frozen lake. But keep in mind, it's a difficult thing to do because there's going to be that slipperiness. If we turn off the slipperiness, it's going to be a lot easier, of course. We can hand code our own algorithm, right? And we can think about how to do that, basically. So, for example, we can take from the book, from our RLAI book, An example algorithm would be SASA. And we can learn how to act correctly. So learn the policy essentially as an output, and then you can try and run that policy. We can also use existing algorithms from Stable Baselines 3 and RL Zoo. So the links are going to be in the slides for those. And there's another set of algorithms called CleanRL that you can also use for gym environments. So in terms of our learning process, we also probably want to try out some other environments as well. So final thing to sort of talk about just briefly is that it is possible to make your own environment if you want to. And just as a brief intro to doing this, you need to make a Python package, obviously. It's in terms of just means making a folder, and the folder has an init.py in it. And then in the init.py, you just say, okay, well, I'm going to firstly import gymnasium as gym and register your environment. So that basically means as soon as your package is imported, then this code will run and it will register that environment to exist. Okay. Now, if you are trying to do a gym.make, as we did, if we just go back a slide or two. All right. Yeah. So when we try and do the gym.make and we put in a string here, right, that string is going to correspond to one of the strings that we've registered. So when we go into our environment registration, that's this string here, that's the initial string. We're doing, yeah. Right, this one here. We also set the entry point. Note the colon there, that's the last little bit, is got a colon on it. That's because it needs to be treated differently, so that splits that up. Now, we then need to have an init.py, and it's going to have something like this, basically to expose our environment. And then the final step is to put in this, to define a class, and the class will start off a little bit like this. So you're going to import gymnasium, and then you're going to define your class, and it needs to be a subclass of gym.env, right? So that's fairly straightforward. And the sorts of things it needs to define are reset function and a step function. So there's a relatively straightforward process to get an environment created of your own. And of course, you might say, well, what can I do with such an environment? Well, you can do anything. You can create an environment that is specific to a robot that you're trying to move, you know, robot arm. And in there, you're going to need to define what actions you can take and what the state space is and all that sort of stuff. So, due to time, I can't cover everything, but I highly recommend that you, well, have a look through these sites. There's a lot more material that I wasn't able to cover. You can read the RLA iBook, which I give a link to here. You can check out the curated papers Spinning Up, which is a resource provided by OpenAI. You can have a look at the Reddit posts on r/reinforcement learning. There's also a Discord channel, and there's sort of many other resources, including David Silver's lectures on YouTube. I really highly recommend. I mean, these days, learning is really open to everyone through these different mechanisms. So with that, I will stop. I think I've got a final slide or two. Really, and I just encourage you to ask questions at this point. I think that, you know, my general overview is that 2 hours is really not enough time to do this subject proper justice. It is an exciting domain to be involved with. I tried to set that this is a starting point for the people here, but don't feel that you have to have understood everything that I've said. It's quite normal that you'll have difficulties and you'll struggle with things. So if you are struggling with a particular thing and you can put it into words, please do ask questions. What I will do while I'm waiting for questions is put the link for the slides in the chat. And notice they may not be perfectly up to date, but they should be pretty close.
Okay, well, thank you very much, James. Very interesting lecture indeed, and we are now inviting questions. If you have put anything in the chat, it would be great to hear it out. Let's just be active on the call. We only have a few more minutes left, but I think it's worth utilizing them. So who wants to break the ice? And thank you for sharing the presentation. I hope everybody can download. Loads of happy people, many deserved congratulations, James, but yet to hear the first question.
See the chat, James.
So there's a question here. Could reinforcement be applied to the sign language production task? And if so, how would you frame the task? Okay, so sign language production. So you're saying that, if I understand it correctly, you are saying how would you get it to correctly produce the right signs? Is it maybe if you can clarify what you mean there? Are you trying to say that so I think it's a really interesting question. I'm not too sure how you would do that. Maybe you could come to me offline about the sign language question, because I'm not too sure I completely understand what you mean by producing it. That would normally be a supervised learning task. If you're just saying translate this vocalization into a sign. So for example, for deaf people, if they were trying to listen to a radio broadcast and it would be sort of visually producing a sign, that would be a supervised learning task.
Okay, we do have another question in the chat. If we look at the neural network diagram, where could annotate the environment as it is usually defined? The owner of the question, please elaborate.
So what was the
question was, if we look at the neural network diagram, where could we annotate the environment as it is usually defined? Right, maybe
so I
maybe
think the question is to do with how does an environment get represented by a neural network. Typically, that's not what we do in terms of reinforcement learning. The environment is actually an environment. So, but you can do this with sort of like a physically inspired neural network. You can actually get the physics to be simulated by a neural network. So that's one possible way you can deal with neural networks and environments. Another issue is that in terms of the internals of reinforcement learning architecture, the algorithm that's learning how to respond to the environment, that will be learning a correspondence of the Q value. So Q, the state action value, how to take a state action and map it to a value. So you think of it as a neural network taking representation of the state and the action and converting it using a neural network into an estimate of how good it is. And for AlphaGo, this is a classic example. This is one of the things that AlphaGo was very good at, that what they're essentially learning is if you take this board position, what we really want to be able to do is, if I move here, what is going to be the new estimated value of that state? And essentially, is it going to cause me to be more likely to win or more likely to lose.
Okay, we've got two more questions. One from Tapello, and I'm going to give him a voice in a second. But before then, there was a question from Samuel. Considering the current volatility in the financial markets, could we still consider reinforcement learning agents to rebalance and optimize investment portfolios?
So with regard to using reinforcement learning for investment, there is a really nice paper, particularly on reinforcement learning in finance, that if the person wants me to share with them, I will happily do so if they send me their email address and make an inquiry directly. But roughly speaking, the main advantage of using reinforcement learning in the context of finance is that you can take account of the friction, the fees essentially associated with different transaction types. So your stockbroker fees are able to be incorporated into your reward function, and that means you can do a good job of that part.
Thank you, James. Samuel has put his email in, and I'll convey that to you. We have Tapello. Please voice out.
All right. Good afternoon. Am I audible?
Yes.
All right. Thank you so much. Thanks for the wonderful presentation. I just wanted to ask can reinforcement learning be applied to sign language production, where sign language production could be defined as you take text or speech and then translate that to signed gestures?
Yes, so I would, the more natural things that would occur to me is to use ordinary machine learning. I'd be very interested to hear if you've got particular things where you think that a reward function could help. But ordinarily, I would start with using a traditional supervised machine learning approach for that problem, simply because it's a more natural correspondence with existing work.
Actually, I think I'm actually starting in this field, and the general approach is that we are planning on using supervised machine learning to address this problem. But I do get a sense and a feeling that it's just a gut feeling that something like reinforcement learning would probably be a better approach to it, especially if you want to maybe create a robot that would sign the gestures that are converted from text or speech to the gestures that a robot would do them. So something like integrating reinforcement learning would be a better approach. It's just a feeling. And maybe I think someone with experience with reinforcement learning could provide the necessary guide in terms of how to implement such a thing. That's why
so to give you an idea of why reinforcement learning might be better is if you can phrase it as a sequential problem, right? So to give you another example, which is slightly different, but sort of gives an example of the sequentiality problem. Imagine that you have ChatGPT and it's having a conversation with you, or you're trying to design ChatGPT to be even better than it was. The point is that a long-term conversation would maybe come out to a better result if you start by asking probing questions earlier on, right? So for example, in a medical diagnosis, if you don't actually say, please ask probing questions to ChatGPT, what it'll do is it'll just produce any old diagnosis. But if instead it was rewarded to think of that longer term goal, right, and to think of the sequence that it needs to go through to get there, then we might end up with a better diagnosis sort of bot. So I think the point about your sign language is what you need to think about is there a sequential decision problem to be made here, or is it just moment-to-moment decisions and then straightforward?
Okay. Yeah, I would have loved to connect in the future so that when I come across such a task, then I would get some advice from you.
Okay.
So I shall be noting the email. James is, or maybe somebody locally can note James's address in the chat.
Yeah. Please do not swamp me with emails.
Yes.
But
However,
I'm absolutely willing to
we are
field
over time.
emails.
We are over time, and we want to thank the speaker again. It was great, and it's a very nice way of closing before a long weekend for Easter and celebrations. Thank you very much, James. Thank you, everyone who stayed online and listened ever so well. Thank you for your questions, and we'll see you at the next masterclass. Thank you.
Bye-bye. Thank you very much.